At EDX Mechanics 1, collisions in 1D, successive impacts with a smooth plane. We've previously discussed the coefficient of restitution E, which is a measure of the elasticity of a collision, and it is a property of a combination of the two materials involved. E equals the separation speed divided by the approach speed and has a value between 0 and 1. Kinetic energy needs to be considered for all the objects together and is usually lost due to heat or sound during the collision. Kinetic energy is a scalar quantity, and a negative answer will indicate a kinetic energy loss. So change in kinetic energy is final kinetic energy minus initial kinetic energy. So if we now consider the impact with a smooth plane. Consider a collision with a fixed, smooth, perpendicular plane. So the plane is perpendicular to the line of motion of the object. Although the plane is fixed, we can still apply Newton's law of restitution where the plane doesn't move. So here we've got a mass of m kilograms moving at a speed u meters per second towards the perpendicular plane, and it rebounds at a speed of v meters per second. So E is the separation speed, which is v, that's the speed of the mass moving away from the perpendicular plane, divided by the approach speed u, which is the speed of the mass as it approached this perpendicular plane. Note, we do not need to apply conservation of momentum when we have a fixed vertical plane. Newton's law of restitution is the method we would use. So in this example we have a mass A which is projected at speed 3 meters per second towards a fixed smooth perpendicular plane. We need to find the rebound speed of the mass. So we can apply Newton's law of restitution, and we can say that E, which is given as a half, is the speed of separation, and we can see from our diagram that the mass is moving away from the perpendicular plane at a speed v, divided by the approach speed, and we can see from the diagram the mass was moving towards the perpendicular plane at a speed 3. So v equals 1.5 meters per second. And clearly, as well as being indicated on the diagram, clearly this must be to the left. We cannot ever have the mass moving through the perpendicular plane. So in this example, we have a ball of mass m which is released from rest at a height of 12.8 meters. We are given that the coefficient of restitution between the ground and the ball is 3/4, and we need to find the height reached by the ball after the second bounce. Gravity, note, is given as downwards at 10 meters per second squared. And although I know the motion is going to be vertical as this ball bounces up and down, I've given the diagram to show that a slight sideways movement to make just for clarity, so you can see clearly the first bounce distinguished from the second bounce to avoid any confusion. So the first thing we've got to do is label up the diagram and find out how fast v, this mass, was moving when it hit the ground. So the initial speed downwards was 0 meters per second. The drop is given in the question, 12.8 meters. And I'm going to show you a couple of methods for finding v. One method would be to use v squared is u squared plus 2as, so go for a traditional SUVAT method from A to B, and it would be sensible to take downwards as positive. So v squared, the final velocity squared from the diagram, is v squared. The initial velocity squared is 0 squared plus twice. The downward acceleration is given on the diagram as 10, and the displacement is 12.8 meters. So v squared is 256 and v is 16 meters per second. We could also find that answer by doing the potential energy lost in the drop is the kinetic energy gained during the drop. So the potential energy lost is m times gravity times h, which is 12.8, and the kinetic energy gained is a half times m times v squared. The mass cancels out and we get the same answer, v equals 16 meters per second. So there are two approaches to finding the impact speed v. Now our fixed plane is the horizontal ground, so the mass is coming towards this fixed plane at a perpendicular angle, which means we can apply Newton's law of restitution at B. So that's the first collision. E is given as 3/4, so I'll put that on the diagram, and we're looking for the rebound speed, which I'm going to call V1. So Newton's law of restitution says the coefficient of restitution, which is 3/4, equals the separation speed, and I can see the mass moving away from the ground at a speed v1, divided by the approach speed, and the mass hit the ground at a perpendicular angle with a speed of 16 meters per second. So the rebound speed is 12 meters per second. So we now have the rebound speed. I'll label it as 12 meters per second. And what I'm interested in now is the speed when it comes back down and hits the ground again. Well, we don't really need to do any mechanical theory to find that answer. If this object rebounds at a speed of 12 meters per second and it moves with no air resistance, it will come back down and hit the ground at 12 meters per second. So I know that this speed here is also 12 meters per second. So that's 12 meters per second. So if it rebounds at B at 12 meters per second, it must come back down to this horizontal ground at 12 meters per second. So there's going to be another collision with the ground at C. E is the same value of 3/4, and so I can reapply Newton's law of restitution at C. So the coefficient of restitution, which is 3/4, is the separation speed. So I'm going to have this mass rebounding at C with a speed v2, so I don't get my velocities muddled up. So the separation speed away from this perpendicular ground is v2, and the mass hit this ground at an impact speed of 12. So v2 is 9 meters per second. We now need to find the height reached after the second bounce. So remember, this is a vertical motion despite the slight distortion on the ground on the diagram. So when it rebounds to the top of this bounce, its velocity will be 0. So again, I'll show you a couple of methods for finding the heights. So the height that we're looking for, I'll put it on the diagram, is h, the height after the second bounce. So I could now do v squared is u squared plus 2as from C to D, and it would be sensible to take upwards as positive this time. So the final velocity from C to D is 0 squared. The initial velocity is v2, which we've just found is 9 squared, plus twice. The upward acceleration, be careful here, is -10, and the displacement is h. So we get 20h equals 9 squared, which is 81. H is 4.05 meters. There's the rebound height after the second bounce. And just to show you a second method there, we could also have done the potential energy gained. The potential energy gain equals the kinetic energy lost. going from C to D. So the gaining potential energy was m times gravity times the height, which is 8, and the kinetic energy lost is a half times m times v2 squared in this case, so that's 9 squared. The mass cancels out and we get the rebound height is again the same answer, 4.05 meters. And that brings us to the end of EDX Mechanics 1, collisions in one dimension.